All right, what is up, AP Precalc? Here's a video I wanted to make a while ago, but this is going to be an intro to Polar, and I'll put this up and send it to you guys hopefully within an hour. We'll take some time in class to go through it tomorrow and just continue building with Polar. So, yeah. This is 4 pages of notes that are introducing polar coordinates, okay? I'll be honest, there's a lot here. Some of it's pretty straightforward. Some of it gets a little bit more difficult, but I'll go through it. Hopefully it'll be helpful, and yeah, we'll keep working through it. And I have most of this done, except a couple examples, I think, on page 2. Okay, so first of all, we have these 4 maps that you can see here, and we're gonna work in both rectilinear XY and polar coordinates this lesson and most of this mini unit. But this question here is, I think, one to maybe just think about when we're considering polar coordinates, which is what's different about these maps. So we've got 4 maps here, loose definition of maps. Maybe take a second, pause this video, come up with 1 or 2 answers, because when we're doing polar coordinates, we're going to be using the same type of visual, but just different formulas and different numbers to analyze those visuals. So what I wrote here, if you just want to consume and not really think too much, is that in these maps we have different ways of describing and moving to locations. We also have, like, this is just black and white, but we have kind of rectangular longitude and latitude. We have some unequal distribution of landmass, right? So the scale is not always the same. Here we've got some color, we got time zone, we have vertical cuts, but nothing really horizontal. Here we have circular maps, right? This is a 2D top and bottom view, polar view, I guess. And then this is kind of a 3D, cut. So yeah, one thing to realize is just with polar, we're gonna have a different way of describing locations on a graph, okay? So our typical way before was this Cartesian coordinate system. We had an X and a Y value, and that would allow us to get to a point. Okay, now with polar, we're gonna have an angle theta, and we're gonna have a radius r. Okay, and the convention is to put the radius first, the angle second. Usually the angle's in radians, that'll be our default. Okay, but that, puts us at the same place. It's just we're getting there a different way. So, the way I normally think about it is move some distance away from the center. That's our radius, and then rotate some angle to get, that contextual point. So, yeah, here's sort of some definitions. The fixed point, what we previously called the origin, is known as the pole. And then the radial coordinate, you guys can read, but it's a horizontal ray, right? So it's a straight, it's not actually really, it's a segment, right? From the pole outward, okay? And if we have those 2 things, we have the distance away from the pole and we have the angle of rotation, we can arrive at the same point. Yeah, so r is our distance, theta is our angle. Here's a view of it in degrees, but like I said, most of the time we're going to be dealing with radians. And again, remember, 0 is straight to the right, and we rotate in a clockwise direction. I guess, we don't have rotary clocks much anymore, but that means, that we're going in the same convention as we go around the unit circle, right? We go up and to the left and just keep mapping around, okay? R can be positive or negative, as can theta. So we just have some different conventions for that. If R is positive, whoops, I did not mean to I did not mean to have my eraser on. If r is positive, then theta is the measure of any angle in standard position that has OP as its terminal side. So we don't have to worry about, for example, going in a negative direction and our angle not really referencing that negative radius. So if r is positive, theta is just the distance between where we start and where that positive radius is emanating from. If r is negative, then theta is the measure of any angle that has the right opposite OP as a terminal side. So for example, if I had a negative radius here, that would still, right, this distance would still be my theta, but now my endpoint would be here. So we have to be a little bit careful if we have a negative radius. Theta is still, the amount of rotation that we do. It's just that we go in the opposite direction from that rotation if r is negative. Okay, and we can have negative theta values also, but that's just a convention if you have a negative radius. Okay, so hopefully that's straightforward for page 1. Page 2, we're just going to do some conversions. Now I've done most of these, but there are a couple that I left. So again, we can have a positive or negative angle. Positive is, the normal way that we rotate around the unit circle, which is counterclockwise. I might have said clockwise before. Sorry about that. This is counterclockwise around the unit circle. Okay. If theta is negative, then we're moving clockwise. So this is the same as our unit circle convention. So this one I've already plotted, but A is the point 2, 120. Right. We're in degree mode here, so we're just going to rotate 120 degrees, we're right there, and then we go 2 units out from the center. You can see that we have a circle of radius 1 here, a circle of radius 2, so that's our final point. 4, negative pi over 2, okay? So we're gonna rotate down negative pi over 2, and then we're gonna go towards that angle, right? So that would be 4 units. Okay. Negative 3, 7 pi over 6. So let's do this live. 7 pi over 6 is right here. Okay, so we're going to rotate around. I'll just draw it and then I'll erase. And then if I go in an opposite direction from there, that means I'm actually going to go away from that negative 7 pi over 6. So I'm going to go towards pi over 6. I'm going to go 3 units. So my final point is going to be right there. Okay? So that is the point. Let me label this. That is negative 3, 7 pi over 6. Why is that? Let me erase this just to make it a little bit cleaner. Okay? And give you guys some time to absorb it. Okay, so why is that correct? Well, to rotate 7 pi over 6, we're going to start at 0. We're going to go all the way around to here. Okay? But because our radius is negative, we're going in an opposite direction, so we're not going, towards that 7 pi over 6. We're actually going in the exact opposite direction, which would be 180 degrees or pi units away, so we'd be going towards pi over 6, right? Those are opposite directions from each other. So instead of going towards there, go towards there, and my radius is 3. Last one, negative 2, 315. Okay, so for 315, that's going to be right here. So we would rotate around towards there, but again, instead of going towards it at a distance or a radius of 2 units, we go away from it. So I need to go 180, 315 minus 180. What is that, guys? That is 135 degrees, right? So 135 is right here. I'm going to go 2 radii towards there. Okay, so that's our point right there. We're rotating around, maybe I'll draw it. We're rotating around 315 degrees. Bam, okay? But then from the origin, because we're going in a negative direction, we go the opposite way, right? Because our radius is negative, okay? All right. Here's some equivalents. I can't even speak. But these are equivalent places, r and theta. That's going to put us at the same place as r and theta plus or minus 2 pi, again, because this is some, full rotation around. If we're in degrees, r theta is the same as r theta plus or minus 360. Okay, and then when we get to negatives, right, r theta is going to be the same as negative r theta plus or minus pi, because if we, move pi radians away, sort of like we did here, pi radians, I know I'm in degrees here, but at 135, pi radians puts us in the opposite direction. Okay, so those are going in direct opposite ways from each other. So the other way that we could do that is just change the radius and make it negative. And then we have the same equivalency for degrees. So these questions, they're basically giving us a scenario, and we want to find an equivalent polar that has, polar coordinate, that has the following characteristics. So if we're starting at 5,300 and we want our angle to be between negative 360 and 0 with a positive radius, well, that means our radius still has to be 5, but instead of rotating 300, how can we get there? Well, we can do negative 60. So 5 negative 60 degrees and 5 300 degrees put us at the same place. So hopefully that makes sense. In part B, now we want a negative radius, but a positive angle. So if we started at 300, well, I'm going to subtract 180 from that. I'm going to go to 120 degrees, and then I'm going to make my radius negative 5. So that's what I've kind of drawn here. So if 300 is here, well, another way that we can get to that location with our angle and our radius is we can rotate 120 degrees, and then we can have a radius of negative 5, and that'll push us, instead of towards this 120 degrees, it'll push us towards 300. So negative 5, 120 is the same as 5, negative 60 is the same as 5, 300. Okay? So I know it's a little bit confusing. You will get it, but it's kind of a new way of thinking. The last one now if we're just going from 360 to 720 with a positive radius, so all we really want to do is, we want to be at the same position as 300 degrees, but we have to have one full rotation first. So all we need to do is add 360 to that. 300 plus 360 is 660. So 660 degrees. That's what I've drawn here. So if this is one rotation, right, around to 300 degrees, we'll take that, but then we'll rotate another 360. So that puts us at 660, and we go in the same direction. So 660 is the same endpoint also. Okay, so actually I think I'll stop the video now, just to give you some time to absorb it. I'll post these notes too so that you can write them up if you want. And then I'll go through converting formulas and the cis notation, which is going to be a little bit trickier, I think. So I'll stop here for now, and I'll make the second video very soon.